Welcome back. So, in the previous lectures we talked about the various hazards. Now, we will come down to some particular important topics, and this is I believe is one of the extremely important part which all of us should know, because the locations of the fault lines in India are not well marked, okay. And we do not have the historical data, or what we call the paleoseismic events, the ancient earthquake data from such fault lines. So, these are there are a couple of areas which are prone to earthquakes, and the most prone is your Himalayas. Okay. So, I'll present couple of examples from Himalaya, but overall I'll try to talk about what are active faults and how we identify that, and what are the importance of that. Okay. This is a beautiful picture which I have taken from the Kangra Valley, where we identified recently a new fault which extends for almost 60 kilometers. We have named that as an Kangra Valley fault, and that fault was not identified before, and our research finding suggests that this Kangra Valley fault was responsible for triggering one of the devastating event in Himalayas, that was 1905 Kangra earthquake. Let us move ahead. So, like what we see in overall deformation, this we have discussed in the previous part 1 of this course, that if you have the deformation going on, then you will, that is in the compressional tectonic environment where we are pushing from both the sides of the plate, okay, then you will have the formation of anticlines, you will have the formation of synclines which goes by side, and finally you will have the breakage or the fracture or the displacement of reaches above the critical point or the threshold limit, it will deform or it will fracture. So, this fractures what we call are the faults, okay, and we will see that what are the we have named it, okay. We have, if I am not wrong, this we have talked in the previous course. So, but we will try to look at the few slides of that, okay. So, we have like deformation will result into, like if I am talking about the compressional tectonic environment, we will have folding, and then finally we have fractures, or we can say the faults, okay. So, we will have this commonly seen in such environment, okay. So, this is an example which has been given, that how rock deforms, okay, and again the rock will deform differently, or it will behave differently at different level or at different depth within the earth surface, okay, or within this earth interior. Now, this is an example of an undeformed rock cylinder here, and this is deformed, and this is getting like it is not completely getting fractured, okay. Now, why it is happening so, the next slide we will talk about. Now, under the different conditions, okay, because the pressure temperature varies as you move into the interior of the earth, okay. So, in some conditions, okay, like what we call the shallow part of the earth crust, if you take a marble, for example, this is a marble cylinder, okay, rock specimen. If you deform at a shallow depth, okay, the pressure temperature will be different as compared to what you see at the greater depth, okay. So, this will fracture as in a brittle form, okay. Whereas, if you deform this in a deeper part, okay, a deeper part, then it will be ductile, okay. So, it will not fracture, it will just deform, okay, with minor fractures. So, these are the variations which one can see, and this can also help in understanding the earthquakes which are taking at the shallower depth, at the greater depth. Okay. So, the earthquakes which are taking, for example, at the shallower depths are more dangerous, okay, because they will result into the fracturing on the surface. So, if you take the deformation in total, okay, one we usually see is the uniform stresses which are observed at the greater depth of within the earth interior, okay, whereas on the close to the surface or in the shallow crust we have directional stress. Okay. So, if you take sigma 1, sigma 2, sigma 3, then we are having uh, the uh, the directional stress. Okay. So, this is your sigma 1, this could be your the sigma 2, and this is your sigma 3. Okay. So, this you are having different stress. Okay. So, depending on that the maximum, okay, then you will have that pattern of deformation or the faulting. So, for example, if you take a rock like in a uniform deformation is there, then you will find that all grains, okay, so you are having this blackish part of the grain, this is the granite, and then we have a quartz, and then we have the whitish part is the quartz and all that, and where this is the mica. Okay. So, if you deform this, okay, which consists like the granite consists of film, quartz, feldspar, and mica, where the mica are the darker ones. Okay. So, if you deform this in differential stress, okay, then this will get preferredly oriented. Okay. This is what the rock has changed. This is a metamorphic rock, granitic gneiss. Okay, this part we have already covered in the previous course. So, it will have, so under the differential stress you will have the major as well as the minor grains oriented parallel to the maximum stress. Okay, fine. Fine. So, this is what we see. So, a very simple stress strain relationship if you look at. So, if you keep on increasing the stress, okay, you keep on building up the strain. Okay, fine. So, eventually all material within the earth or at the earth surface, okay, are having some plasticity. Okay. So, initially it will deform, okay, elastically, then you will have ductile, and then finally you will have the fracturing. Okay. And this fracture, what we see is your rupture. So, if there is a sudden displacement, then this will result into an earthquake. Okay. So, earthquake is a sudden release of the energy which has been stored. Okay. So, this is what we talk about. Okay. So, strain is building up along the plate boundaries, and finally it will be released. Okay. And that release will be in terms of what we see, the fracturing or faulting. Okay. So, this fracturing for us, we take this as an faulting. So, faults, if you look at what we usually define, a fracture in rock along which block of rock slip past each other, okay, is termed as fault. Of course, the question may be asked that there are many such fractures which will show displacement. Okay. Should we call those as in faults? We will say yes, okay, but they are not seismogenic faults. Okay. If they are not going to trigger any earthquake, then we will say they are non-seismogenic fault. They could be related to some deformation, they could be related to some other reasons like subsidence and all that, but they are not exactly the deep-seated faults which are responsible for triggering the earthquakes. Okay. So, faults mainly occurs within as in fault zone, known as what we call the within a zone or along a zone, which we call as a fault zone. Then surface along which the block of rock slip is called as fault plane. We will see those what is fault plane and all that. Okay. And the surface manifestation of such displacements are termed as fault scarps. Okay. So, if we look at just a small sketch here, then what we see is that suppose this was in flat area and there is a fault here which will move like this, then what we see is something like that. Okay. So, this fault has moved the surface. So, this was the surface here, this was the surface, and this has moved up. Okay. So, this movement along which the land moved, okay, is termed as fault plane, okay. And the expression this is on the surface is termed as fault scarp. We will see some couple of examples of this. Okay. So, naming fault, usually what we do is we take into consideration that how it has slipped. Okay. So, on the basis of one, the depth of the fault, what is the angle of the fault plane mainly, okay. Then we say that in which direction it moved, whether it moved laterally, it moved up or it moved down, then sense of offset, whether it is a right lateral or left lateral. Okay. Then from this we can establish the direction of displacement, okay. Because this information is extremely important for the civil engineers or for any person who are involved in town planning. Okay. So, and the sense of displacement, then we can talk about the amount of magnitude of displacement. So, how much it moved, okay, whether it moved for centimeters or it moved for a couple of meters. Okay. So, that is extremely important for us to be noted down. So, if you have this information, from this information you can gather or identify this all parameters. Okay. So, with this let us move ahead, that how we will be able to differentiate between the different type of faults and how we can determine the sense of offset or the sense of displacement. Okay. Now, mostly what we see is that fault has been like categorized based on the slip, and the slip is the actual relative displacement between the two blocks. Okay. So, on the basis of the sense of slip, the faults are been categorized as either the normal fault or the strike slip fault or thrust faults or reverse fault. But in the major category, if you look at what we identify or the categorize is either it is a strike slip fault or it is a dip slip fault. So, in previous part, what we talked about, that one is the strike. We have a strike of the fault, and then perpendicular to this will be your dip. Okay. So, this is your dip and this is your, this I am talking about the plan view, and this is your strike. So, if the movement has occurred along like this, okay, sorry, the movement has occurred along the strike, then we call that as an strike slip faults and all that. Okay. But if they are the movement is occurring along the dip direction, okay, then they are dip faults, dip slip faults. So, if you just look at the block here, okay, I will just put very quickly. Okay. Suppose we are putting a block here. So, this is the plane we are having. Okay. So, this what we have is the this is your fault plane, okay, and these are the blocks which were together once. Okay. So, the movement has taken place along like this. Okay. So, this is the dip plane you are having. Okay. So, this is the dip direction. So, if you take this here, this is your strike and this is your dip direction. So, movement has occurred along the dip. Okay. So, this we classify as a dip slip faults. Okay. But suppose the movement occurs along the strike, okay, then we say that as in strike slip. So, let us see more signatures of this. Okay. So, in short, broadly we will classify the faults based on the dips, based on the slip, that is either the slip is along the strike or either the slip is along the tip. Okay. Now, parts of the faults, what mainly we look at the previous part I was talking about, that we have some which are measured with respect to the horizontal, some are measured with respect to the vertical. Okay. And in the previous course we have talked about that with respect to the horizontal, if we measure, this is what we are having, the dip of the dip here. Okay. So, we have the dip with this, that is with respect to your horizontal, that is the angle. Okay. And then we have the heave again. So, heave is the horizontal component of the dip, okay. That is the horizontal movement or how much we are taking place. Okay. There is a separation of the land. So, when the tube, this surface is moving here, like, okay. So, then we are having a horizontal component also, so that will be in heave. Okay. And the angle with respect to the horizontal, that will be your dip direction. So, this angle, if you are having the fall plane is here, then the angle here will be your dip amount, and the dip direction will be like that. Okay. So, this is an horizontal separation, which is termed that it gives the amount of land shifted sideways. Okay. Then we have throw, that has been given by here, the T is an vertical component of the dip separation, and that gives that the how much amount the land has moved vertically. Okay. And then we are having head, again that is an angle of the fall plane with respect to vertical. So, this is an head here. Okay. So, this is with respect to your vertical, and then we are having dip with respect to the horizontal, that is the amount of the angle. Okay. So, we are having this is what we to the different parts. So, mostly when we come across any fault, okay, so we try to measure the so these components. Okay. So, we have heave, throw, head, deep, and then if we come across, for example, if we are able to see some layers here, okay, like for example, one is here and another one is here, okay, then we can say that this is the net slip. Okay. So, this is the net slip what we can measure. There is another well explained diagram which talks about the another component when you are having the dip slip also and you are having strike slip also. Okay. So, if you are having combination of both, then you will come across one more component which is termed as a rake, and the rake is the slip direction of the hanging wall block measured in the fall plane, okay, and from the dip factor. So, this is the rake what we are measuring here. Okay. So, other parts are also given here, like we are having net slip. So, net slip is your this one, how much it slipped, because this block slipped laterally along the strike as well as in the dip direction. Okay. So, this is the net slip what we are having. Then we are having dip slip. Okay. So, dip slip is like what we are having this one. Okay. So, this is the amount of dip slip we are having, and this is measured from the tip of this and then tip of this one. Okay. So, this is the dip slip amount which we have. Then we are having the strike slip. Okay. Strike slip is this one. Okay. So, along the strike how much it moved, that is C. Then we are having D, vertical throw, as we were talking about. So, this is the vertical throw we are having. Okay. Then we are having E, the horizontal throw, how much is the horizontal throw here. So, this is the horizontal throw we are having. Okay. Then heave, again that is the horizontal component. Okay. So, we are having the heave is this one, this is F. Okay. So, we are having this the heave. So, the strike slip faults, if we look at, then what particularly we are looking at is those faults that accommodates horizontal slip between the adjacent block along the strike of the fault line. And the dip slip faults further we classify as whether it has the block has moved upward or the block has moved downward. Okay. Based on that we classify that as a normal fault or we say they are the thrust faults or the reverse faults. Okay. Now, depending on the angle of the fault plane, we classify that either the normal slip fault was steep angle fault or it is an low angle normal fault. Where is now, so this fault will usually seen in the extensional tectonic environment. Okay. Whereas this two are mostly seen when we are having compressional tectonic environment. So, we are having compressional tectonic environment, if we are having extension tectonic environment, where we will see the normal faulting. Okay. So, again on the basis of the regional understanding of the structural or the tectonic framework, one can judge that what type of faulting you will expect in that particular region. Okay. And if you are having an oblique, then you will have the strike slip one. Okay. So, mostly in Himalayas we see that this is the pattern of deformation, and we will come across mostly the thrust faults and we will come across the reverse faults. So, thrust faults are the faults which are having dip less than 45 degree. So, the fault plane will have the dip of less than 45 degree. If it is greater than 45 degrees, then they are termed as the reverse faults. Now, coming to this active faults. Okay. What are the active faults? Usually what is been seen, that keeping in mind the hazard which has been posed to the human settlements. Okay. Based on that, we have identified and we have classified these faults as an active faults. These are the faults along which the movement occurred during last 10,000 years and likely to occur in near future. Okay. So, this is very much important, because there is a likelihood of having an earthquake of large magnitude in near future along this fault. Okay. And the manifestation of these are the active faults which have the manifestation of crustal deformation, which are seen on the surface in form of displaced landforms. Okay. These are considered to be the source for large magnitude earthquakes in near future. It is vital for the hazard assessment. Okay. And as I told that this active fault information is not available from much of the part from India. Okay. And recently the Ministry of Earth Science has floated a program of mapping of active fault in Himalayas, in Kutch region and all that. Okay. So that we can come up with an digital active fault map of Himalayas and Kutch region, because these are the areas where we have experienced large magnitude earthquakes during recent historic past. Okay. I will stop here and we will continue in the next lecture. Thank you so much.